recording. Here we go. We're doing 1B.5 part B, polynomial functions in complex zeros, okay? So we know that polynomial functions are either going to be odd or even, right? In a sense of their degrees, correct? All right, there's also when we refer to odd and even in terms of their symmetry, meaning how do they behave around the origin, okay? How are they acting around 0, 0? An even functions are going to have even behaviors, okay? So essentially a function f is even only if when the point xy is on the graph and so is negative xy, okay? Meaning that I'm equally split between the x and y axis. So for example, this quadratic here, if I have on this side negative 2, 1, that means that I also have on this side positive 2, 1. Does that make sense? Okay, it's even. It's symmetrically split with the y-axis, okay? That's an even function. Algebraically is what we're focusing on proving. So in Algebra 2, we more so focus on visually proving whether it was odd or even symmetry. Does y'all remember that? Okay. And pre-cal, we focus on the algebraically proving that they are. To algebraically prove that they are even, we are essentially going to set these two equations equal to each other. And if they simplify to be exactly the same thing, then this shows and proves that this is an even function. Okay. So it's not a calculator problem. It's not a graph and check problem. It's an algebraic problem. All right. All right. A function is odd. F is odd if and only if when your xy has the corresponding negative x, negative y as part of the function. Okay. So when we are looking here, I'm going to, oops, that is not a very straight line. We're going to pretend that that's straight. Okay. We have this cubic function here. It's going to go through the origin. And notice here, I have 1, 1, 1. I also have negative 1, negative 1, negative 1. Okay. I have both parts at every point this happens. Okay. So algebraically, we would prove that if I substitute a negative x and I distribute a negative across the function, they are algebraically equal. Okay. So again, in Algebra 2, we focus on visually proving odd and even symmetry. And then now we're focused on algebraic, okay? Another key thing for even functions, just remember that they're going to be symmetrical. I can spell. Symmetrical with the y. Okay, they're symmetrical around the y-axis, not the x-axis, the y-axis. Okay, odd function, they have they are not symmetrical necessarily. They have rotational symmetry, so it's rotational through the origin, meaning that if you were to take your paper and you rotate it 180 degrees, your function would still look the same. All right, so those are kind of your tips on visually recognizing and algebraically. So we're going to first start with visually recognizing, okay? So if we look up here, we have A, B, and C. We're going to identify whether it is even, odd, or neither, okay? So for A, is it even, odd, or neither? It is odd, okay? First thing we want to check is, does it go through the origin? Does it go through the origin? Yes, it goes through the origin, right? Second thing we want to check is that corresponding points are on the graph. So notice here we have negative 1, positive 2, and here we have 1, negative 2, right? And that pattern continues. Your last quick check is if you take your paper and rotate it 180 degrees, go ahead and do it. Rotate it 180 degrees, which means turn it upside down. Does it still look the same? Yes. Everyone sees that? All right. B is B odd or even? It is even. Okay. We know that it's even because it has symmetry with the y-axis. Okay, it is literally symmetrical with the y-axis. That is your visual representation. Okay, on C here, are either one of these satisfied? No, even though it goes through the origin, it does not have rotational symmetry, right? And because of that, this is a neither case. Okay, how do we feel about being able to visually recognize odd, even, and neither symmetry? Good? Doable? All right. Let's talk about it algebraically. Okay, so now we're going to look at it algebraically. When you have an algebraic problem and it's asking you, that means this is going to be on a non-calculator part of your test. Okay, you can't graph and then tell me that it has rotational symmetry through the origin, or look at it and say it has symmetrical symmetry with respect to the y-axis. Okay, this is where our rules come into play. Okay, so the first thing that you're going to always check for is the degree of the function. All right, the degree tells you whether you're testing if it's odd or even behavior. Okay, even degree functions are going to be possibly even symmetry. Make sense? Odd degree functions are going to possibly be odd symmetry. Okay, so the first thing you check for is the degree of the function. So the degree of this function is what? It's a second degree polynomial, right? Because it's a second degree polynomial, I'm going to do the even test. Okay, the even test is that f of x equals f of negative x, which means that if I plug in a negative x into this function, it is still going to look the same when it's all said and done. Okay, so my end game is to get this result by plugging in a negative f of x. If I do, then it's even. If I don't, then it's neither. Make sense? Okay, so we're going to find f of negative x. So f of negative x equals, everywhere there's an x, I'm plugging in a negative x. Okay, so we have negative x squared plus negative x minus 12. Keep going. A negative times a negative is a positive. A positive times a negative is a negative. Are these two identical? No. So therefore, this is a neither. Oh, forgot. That is the no-go writing zone. And we still do not know why. Okay, was that terrible? It was doable, right? All right, so that's how you do it for an even. Now we're going to look at an example for an odd. I'm going to draw a line so that my work doesn't overlap. All right, so again, first you're going to look at the degree of the function. The degree here is fifth degree. Because it's a fifth degree polynomial, I know that I'm going to be following the odd rule. I'm testing to see if it is odd, okay? The odd rule is that f of negative x equals negative f of x, okay? Odd testing requires 2 steps versus even testing only requires 1 step, okay? For odd testing, you have to find your f of negative x and your negative f of x, okay? And then compare if they're the same or not. All right, and I'm gonna be very honest with you, in your notes, I did not give you enough room to do this. So if you need to get a Post-it note out of the bin and add it on there, you may want to do that because you're not gonna have enough space to do both unless you write super duper tight. All right, so first up, I'm gonna find f of negative x. So when I substitute negative x into here, what do I get? Well, this equals negative x to the 5th minus 4 times negative x to the 3rd. I'm going to simplify. A negative times a negative times a negative times a negative times a negative is still going to be a negative. Does that make sense? Same thing here. A negative times a negative times a negative is a negative, but there's a negative 4. So negative 4 times negative x is going to make a positive 4x cubed. So my f of negative x equals negative x to the 5th plus 4x to the 3rd. So I checked this. I found this one already. Now we're going to do negative f of x. When you have negative f of x, that simply just means that you are changing the sign of every term, right? You're taking the entire function, x to the 5th minus 4x to the 3rd, and you're just distributing the negative. When I distribute that negative, I end up with negative x to the fifth plus 4x to the third. Now I ask myself, are they the same? Does f of negative x, which equals negative x to the fifth, plus 4x to the third equal negative f of x, which equals negative x to the fifth, plus 4x to the third? And the answer is yes, they're the same. Yes, they are equal. So therefore, this is odd symmetry. Because they are exactly the same. Yay, nay. Okay. All right. So I'm going to give myself a little more space so that I can do it again. So I'm going to just go to the next page. Is that okay? All right. So I'm going to do C. First, again, you're going to check for the degree. What is the degree? It's a fourth degree polynomial, which means that I'm going to be doing the even test. The even test says that f of x has to equal f of negative x, okay? We already have our f of x, right? So it gave us our f of x, bam, f of x is done. What do we just need to find? F of negative x. So we have f of negative x equals, and everywhere there's an x, it's going to become a negative x to the fourth minus 6 times negative x squared equals a negative times a negative times a negative times a negative is a positive. Okay, a negative times a negative is a positive. A positive times a negative is still a negative. Okay, so you ask yourself, does f of negative x equal, does this equal that? Yes. And because it's a yes, that means that this is even symmetry. Ta-da! You did even symmetry. How do you feel about going from just visually, graphically telling me to being able to do it algebraically? Okay? Doable? All right, it's like playing like a weird game of concentration. Is that a pair? Do they match? If not, then no. Try again. Next person's turn, right? That's how I view it. Will you view it that way? Probably not. But I feel like if you, lie to yourself and make it into a game, it'll make it better. Okay. Continuing. Okay, wait. My ADHD brain. All right. So here we go. We have p of x. So this polynomial function is 3x to the j plus 2x to the k, where j and k are real numbers. What should the values of j and k be so that we can have an odd function? All right. So I'm going to pause and I'm going to let you guys kind of talk about it at your table. Remember, the rule for it to be an odd function is that your, where's my little pin? Your f of negative x has to equal your negative f of x. So at your groups, I want you to take a moment and consider what would j and k have to be in order to produce an odd function. I will allow you to test out your theory and your numbers using a calculator. So if you want to use the Desmos or use a handheld to see what possible j and k values could be to make it true, go for it. But I do want you to try and attempt for the next 3 minutes. Cool? All right, here we go. All right, so who would like to share what they got for J and K? We got a 5 and 3. So we have J equals 5, K equals 3. So we end up with P of x equals 3x to the 5 plus 2x to the third. All right. If I was to plug in a negative x, then it would come out as a negative 3, right? If I plug here, this will come out as a negative 2. So, okay. So P of negative x would equal negative 3x to the fifth minus 2x to the third. And that's a funky looking p there. Okay. And now if I found px negative p of x, that means I'm changing the signs of each one of my terms, right? That's all you're doing when you're multiplying a function by a negative is changing the signs of all your terms. So we have negative 3x to the fifth minus 2x to the third. Does that work? Yes, they are equal. So possible values would be j and k would be 5 and 3. This is your secret. This is your hint. In order for it to work, those powers just have to be odd. Does that make sense? Yes. They just have to be odd. So whether it was 5 and 3, 7 and 3, 9 and 3, the powers just have to be odd. Okay? The reason being is because when you do the multiplication of a negative, it's going to maintain that sign all the way through because you're going to always have an odd negative out, right? Which is going to make everything. You know, one negative can ruin a bunch. Life lesson right there. Okay? All right. So up next, difference to determine degrees. We did this in algebra too. Okay. Do you guys remember when we found the difference between our dependent variables and each level of difference told us what degree of polynomial would be? Does that ring a little bit of a bell? Yes. Okay. So don't say, Ms. Jones, we didn't do this. I will pull up the notes and show you in pre-AP algebra 2. Okay. So that's all this is a review of that concept. Okay. If you're given a table of data and your key thing is your x values have to be in consecutive order. Are my x values in consecutive order? Yes. I can then use the difference rule to figure out what degree of polynomial this is. Okay. If it's the first difference, then it's a first degree polynomial. If it's a second difference, it's a second degree polynomial. Third difference, third degree polynomial. Okay. So let's test it out. So right here, negative 30 and negative 14. So remember to find your difference. Your difference equals your y2 minus your y1. So negative 14 minus negative 30. Negative 14 minus negative 30 is going to be a positive 16. Okay. Negative 12, because it's my second y, minus my first y. So negative 12 minus negative 14, which is negative 12 plus 14, which is, it would be a positive 2. Okay. Now we're at negative 12 minus negative 12. What is that? 0. Now we have negative 2 minus negative 12. It's going to be a 10. If you need to write it out, no one knows what you write on your paper. So if you need to visually see 30 minus negative 2 and write it out to know that that's 32, do it. Okay. If you need to visually see 96 minus 30, write it out. It is your paper. It is your notes. It is there for you. Okay. So this is my D1. Is D1 the same? No. So therefore, we know it's not a first degree polynomial, aka a linear model, right? Do you remember now? Yes. Okay. I told you I didn't lie to you. Now we're going to do our D2. 2 minus 16. And again, if on your paper you need to write it to see it, write it to see it. 2 minus 16 gives us negative 14. 0 minus 2 gives us 10 minus 0 gives us 32 minus 10 gives us 22. 66 minus 32 gives us, is D2 the same? No, because D2 is not the same. It is not a quadratic model. Make sense? All right, now we're going to keep going. Negative 2 minus negative 14. We get 12. 10 minus negative 2. 22 minus 10. 34 minus 22. 12. Is our D3 the same? Yes, our D3 is the same. So this is a third degree polynomial. Ta-da! Do y'all remember doing that? That's why we're just going to show it, model it, and move on. I put this in here because I don't want to assume that I can assume for the ones who had me that we taught this, but if you're coming from another teacher, it is not fair to assume that you know that knowledge as well. Does that make sense? So that's why it's there. So that's why we had to go over it. But now, do we all know it? Can we all use the rules of difference to determine the polynomial? Yeah? All right, cool. Okay, so it says here, next, sketching a graph with repeated values. This is an example of multiple non-calculator questions you may have. Normally, they will be multiple choice, but this would be on the non-calculator part of the test, okay? Remember that our test is 60% non-calculator, all right? So we have to be strong at being able to do things without a calculator, okay? All right, so up first here, it says, we're going to write a polynomial function of minimum degree whose zeros include the following. All right. So up first, it says that we have x of -3. It has a multiplicity of 2. We have x of -1 and x of 4. X equals 4. Okay. Remember, when you're giving your x's and your factors have a relationship, right? They are opposites of each other. Does that ring a bell? Okay. So when I have a x of -3, that means that its factor is x plus 3. Yes. Okay. The multiplicity tells you the power of that factor. My multiplicity is 2, so my power of my factor is 2. Still with me? All right, on to the next one. We have x equals -1. The opposite of -1 is x plus 1. It has just a multiplicity of 1, so there's no power on my factor. Make sense? All right, on to the next. X equals 4 has a multiplicity of 1 as well. So again, it's a positive 4, so my factor is going to be a -4. All right. It tells us that our a is greater than 0, which just simply means that this is a positive function. So this is the f of x that we created. All right. It's a positive function of what degree? It's going to be what? So remember, your degree is based on adding all of your multiplicities together, right? So I have it. Casper the Friendly One is there, so don't forget Casper. So we have 2, 1, and 1. So what degree is this? It is a 4th degree polynomial. Do we see that? Okay. Your degree is based off of the multiplicities of your factors, of your x's, of your zeros, whatever word you want to use, but it's based off the multiplicities. Okay. All right. So now that we have this, we now can create our table. So all we're doing here is evaluating these given x values into this function. Make sense? So we're looking for f of -4. When I plug -4 into here, what do I get? -4 plus 3 is, and again, if you need to write it out, no one's going to see your paper. It's your notes. It's your brain. So over here, I have -4 plus 3 is -1. -1 squared is +1. Makes sense? On to the next. Plug -4 in. -4 plus 1 is -3. On to the next. -4 minus 4 is, you owe me $4. You're like, let me borrow another $4. You now owe me $8. And I want all my money back. Okay. So multiply. 1 times -3 is -3. -3 times -8 is +24. Yeah. All right. Anyways, here we go. So do we understand how you're filling in the table? All right. I'm going to pause for a moment and I want you guys to fill in the table values and then you're going to tell me what they are so that you can do it on your own, because otherwise, if I stand up here and do it, you're just going to keep watching me and you're not going to plug in the values yourself and practice your mental math skills. So guess what you're going to do right now? Practice your mental math skills. Go.